Well, hello. Today we're going to be talking about chemical equations, being able to interpret chemical equations, being able to use the diffractions, yeah, to be able to interpret the chemical equations. Before we get into the crazy German accent, just to back up, this particular objective kind of sounds a little confusing when you read it. What do I mean? I have to interpret a chemical equation in terms of moles and molecules. It's really not that bad once you understand what the objective is asking you to do. We've been writing balanced equations for a little while now. I've got an example of one on here, the formation of water. So synthesis of water, 2 hydrogen molecules plus an oxygen molecule, 2 water molecules, right? So when we write a balanced equation, what does that mean? What does that really tell us? And that's what this whole little presentation here is about. So we can interpret this equation a few different ways. So we could say this on an individual atom-to-atom level, that literally 2 H2 molecules are reacting with 1 O2 molecule to produce 2 H2O molecules. It's true, however, that's so small that we would never be able to see it. It's not really a feasible amount of chemistry for us to happen, but chemistry really does occur at the atomic level like that. So the second one, we could say we can group things of atoms. We could say a dozen or 2 dozen hydrogen molecules reacts with 1 dozen oxygen molecule to give us 2 dozen water molecules. Or more importantly, the last one, right? We've been talking about this beast before. There it is, it's back, the mole. A mole member is just a group, really big group, but a group that we can see. So a mole of oxygen reacts with 2 moles of hydrogen and produces 2 moles of water. All of those work. Remember, when we're talking about describing a reaction like this, we can use that language for either reactants or products. So we can say that, yeah, if we need 2 moles of water, we will need to be able to react 2 moles of hydrogen, 1 mole of oxygen. So we can kind of go either direction with those. How do we get that information? And you probably already figured it out. It's that coefficient. We have to have a balanced chemical equation in order to be able to realistically picture what's going on in that chemistry. So the chemistry is the really important part. You got to balance that equation. And it's the coefficients, those numbers out in front. But what the coefficients are, shortcut, coefficients are a mole to mole ratio. And you can see I've got that sentence written down right in this kind of zone down here. 2 moles of hydrogen react with 1 mole of oxygen to create 2 moles of water. It's critical that you balance your equations. You must balance. You always have to look first. Because otherwise, if you don't balance your equation, every reaction looks like it's a 1-to-1-to-1 reaction or ratio. You got to balance it first. And that's going to be the hardest thing for you guys sometimes to remember, is to actually stop, balance, and then go check to see what that mole-to-mole ratio is. So here's one for you. You're going to click on pause. You're going to take a look at this, see if you can figure out what the response is. I need you to be able to state the meaning of the following reaction in terms of moles of reactants and moles of products. So the reactants shown there, it's nitric oxide, NO, plus hydrogen gas, H2, yields N2, which is nitrogen gas, plus liquid water, liquid H2O. So see if you can fill in the blanks in that particular sentence right down there. I've got a sentence form for you to kind of fill out, but don't forget, got to balance the equation first. Hit pause, and then we'll move on. Welcome back. Did you get it? So in order to balance the equation, here is our things that we need. We've got to have 2 nitric oxide molecules, 2 hydrogen molecules, and we'll eventually produce 1 nitrogen. There's no 1 in front of it, and then 2 liquid water molecules. So there's kind of a little picture of what it looks like. Blue is supposed to be, blue or green is nitrogen, white's hydrogen, yellow is oxygen, just in kind of a general thing to do it. So we would read that sentence like this. 2 moles of NO react with 2 moles of hydrogen to produce 1 mole of nitrogen and 2 moles of liquid water. That's what you need to be able to do for this objective, be able to read a balanced equation and kind of give me that mole-to-mole ratio when we're doing a balanced equation like this. So let's move on and think about using this. Why do we care, right? This allows us to make predictions about quantities. So if I start with 2 moles of hydrogen, for example, and this is I'm kind of in that easy one right here. So if I start with 2 moles of hydrogen, it's pretty easy to say I can produce 1 mole of nitrogen, since that's what our reaction says. We've got 2 moles of hydrogen, so I'll be able to do 1 mole of nitrogen. Unfortunately for us, of course, it's not always that easy. Sometimes we start with not so round numbers. The harder example here. What if I start with 4 moles of hydrogen? Our equation up here has 2, but I have 4. So it's kind of double, right? If I double the amount of hydrogen, then I should be able to double the amount of nitrogen. I should get 1 nitrogen, but since I started with double the amount of reactants, I should get double the product, and I will end up with 2 moles. Makes pretty good sense so far. However, Gets trickier yet, right? Of course it always does. So the last one. What if I start with something less obvious, like 0.5 moles of hydrogen? Still not too challenging yet. I know you could probably kind of logically figure it out. But if I had 0.5 moles of hydrogen, my ratio is 2 to 1. So if I have 0.5, it's a quarter of my hydrogen, so I would get a quarter of my nitrogen. So I'll get 0.25 moles of nitrogen gas. Or I could say it's in a 2 to 1 ratio. 0.5 is double. The single would be 1 would be 0.25, kind of in a 2 to 1 ratio. 0.5 is 2 to 1 to 0.5. I don't know. Anyway, there's some different ways to think about it. I really prefer thinking about it with the Wunderfraction. Yeah, always we use the Wunderfraction to solve these problems. Very important to use the Wunderfraction. Look how much easier this is rather than the kind of the logic jumps that you have to make. Well, it's a half, or it's a quarter, or it's 2 to 1. This makes it very straightforward. The question says we have 0.5 moles of hydrogen. Again, when we set up our wonder fraction, you start with what you know. I'm going to start my little wonder fraction with 0.5 moles of hydrogen. And then this next step here is our stoichiometry step. This is the step where I'm using the balanced coefficients, 2 hydrogens and 1 nitrogen. And I plug them in just like any other conversion factors, like 12 inches equals a foot. Well, 2 moles of hydrogen equals 1 mole of nitrogen in this case. And then we just carry it out like a regular Wunderfraction, and this allows us to do a nice, really easy answer. Calculator can solve it for us, and we get 0.25 moles of nitrogen. But remember, has to be a balanced equation. You can only use multiple ratios with the Wunderfractions, yeah, if the equation is balanced first. So, next example, right? Same exact equation, a little bit harder number, right? Not quite so easy now. 4.7 moles of nitrogen gas. Now it's kind of really not obvious. Now I'm actually starting with a product. Did you notice that? Starting with 4.7 moles of nitrogen, and I can predict how much product I need, or reactant I need. And that's okay too. Again, start with what you know. 4.7 moles of nitrogen. That's our starting point. And then right here, there's our conversion factor. How did I get that? Right here. Our ratio is 2 moles of NO to 1 mole of N2. Again, so there's our 1 mole of N2 on the bottom, 2 moles of NO up on the top. Again, why is it there? Because our units need to cancel out. The nitrogen here has to go down to the bottom, and that's why nitrogen's on the bottom of the next step. Do your math. You realize that you end up with 9.4 moles of NO. Wouldn't have been obvious if someone had just asked you that. Much easier to do it with a calculator, so let's let the calculator do the work for us. As long as you know how to do some Wunderfractions, it's pretty good. I think it's your turn. Yep, there we go. Your turn. Interpreting this equation. Let's see if you can solve this one. This is the actual equation for formation of a type of rust. You've got the relationship between FeO, which is iron 2 oxide, reacting with oxygen to form rust, iron 3 oxide. So here's your question down below. How many moles of oxygen gas is required to react with 2.4 moles of iron 2 oxide? Now it's your turn. You need to hit pause. See if you can work this problem out on your own. It's a Wunderfraction starting with 2.4 moles of iron 2 oxide. Your turn. Welcome back. Number 1, check out the sentence up in red here. If you forgot to balance the equation, you better hit pause again. You need to go back and balance that reaction before you look at anything that's down below here. Otherwise, you're cheating. No, no, no. So balance your equation. You got it. Right here, when we balance it out, we've got 4 moles of FeO, iron 2 oxide, are going to react and produce 2 moles of iron 3 oxide, Fe2O3. So when we do that, once you've got the equation balanced, it's as simple as a Wunderfraction. Yeah, 2.4 moles of iron 2 oxide. Here they are. And then we use our conversion. These react in a 4 to 1 ratio. Why is it 4 to 1? Why did I put the O2 up here? Because the equation asked me for oxygen gas. It didn't ask me for how many moles of iron oxide, iron 3 oxide that I produce. It asked me about oxygen gas. That's what I was trying to find. So that's why that is up on the top up here. And again, the coefficient, 4 is the coefficient down there, and 1 is the coefficient in the equation for oxygen. So by the time you do the math, your answer is 0.60, 2 sig figs. 0.60 is 2 sig figs. So that would be our final answer. So there you go. That's how to interpret balanced equations in terms of moles, and to be able to use a simple Wunderfractions, yeah, to predict either how much reactant you need or how much product you need, given number of moles. See you in class tomorrow.